we observed for a capacitor with a capacitance C of 0.47 farads. Remember, capacitance is voltage divided by charge, charge divided by voltage, Q over V. So that's 0.47 farads. Q is in coulombs, V is in volts, so it's 0.47 coulombs per volt. This means that we're storing 0.47 coulombs of charge for every volt across the capacitor. Now we use the voltmeter and we observe that the voltage at time t equals 0 was 5.17 volts. After 20 minutes we observe that the voltage was 4.9 volts. So it's fallen from 5.17 to 4.9 volts. The voltage as a function of time, of course, is C e to the negative t over RC. Now let's just look at how this function behaves for a second. As t gets bigger, this exponent gets larger in magnitude, but it's negative, so that e to that exponent is going to get smaller, since e to a negative large number is very small. Remember, e to a negative number is 1 over e to the number. Given this functional relationship, and again, this is something that general college physics students should know and understand. Principles of physics students, depends on your mathematical background. If you can follow this, you probably should, just to pick up some applications of the mathematics. But this requires a good knowledge of pre-calculus, okay? Now, we're taking our information. V of 0 is 5.17 volts. Okay, now, V of 0 also has to equal C e to the 0, since t is 0. So we get C e to the 0, which is C, so that we see that C, or we find that C, is 5.17 volts. Now we know that our function, well, is going to be C e to the negative t over RC, where C is 5.17 volts. It'll be 5.17 volts e to the negative t over RC. Now V at 20, and of course this is 20 minutes, equals C e to the negative 20 over RC. Now if C is 5.17 volts, then this is what our voltage ought to be at time t equals 20. We can set then 5.17 V e to the negative 20 over RC equal to 4.9 volts and solve the equation for RC. Once we find RC, of course, knowing C to be 0.47 farads, we can find R. Okay, so this is negative 20 over RC is going to be the natural log of 0.95. We get this by taking the natural log of both sides, which is how we solve an equation where our variable is in the exponent. So using that standard technique, we obtain this solution, or partial solution. Then we solve for RC. If negative 20 over RC is a natural log of 0.95, RC is going to be negative 20 over the natural log of 0.95. Now 20, remember, was 20 minutes. We didn't really carry the unit along with this, but we're going to recall that 20 was 20 minutes. Natural log of 0.95 is about 20. So we get negative, or about negative 1/20th, I'm sorry. And when we divide this, we get about 400, and that indicates 400 minutes. So that RC is 400 minutes, which of course is 24,000 seconds. Now we change this to seconds because seconds are the standard units in which we measure our physical quantities, especially voltages and currents and so forth. So the R is 24,000 seconds over 0.47 coulombs per volt. Now if we're careful about the units, remember that a volt is a joule per coulomb. So what we have is seconds over joules. I'm sorry, that's a joule per coulomb, so that's coulomb squared per joule. Any case, I haven't gone through the details of the units, but if you do go through the details of the units, you find that you end up with ohms, which are units of what? Those are units of voltage over current. Okay? So it's like volts per amp. Down here, okay, well here we determine that the resistance is about 50,000 ohms. Down here we see that RC is the time it takes to fall to 1 over E, approximately 1 over 2.7 or 0.37 of the original value. That is, if T was equal to RC, what would we have in the equation? The equation is V is C e to the negative T over RC. If T was equal to RC, this would be C e to the negative 1, which would be C times 0.37, or since C is the original voltage times 0.37. So that, again, RC is the time it takes to fall to this fraction of the original value. And at about 0.7 RC is the half-life of the circuit. RC is called the time constant for your circuit.